So good morning, everyone. So basically, this chapter name is Virtual Inertia-based Stability and Regulation Support. So this chapter is the continuation of the last two lectures that we have seen. And so first, we will recap the important points and concepts of last two lectures that we have seen. In the first lecture, we have seen general structure of inverter interface, distributed generators, and control methods of grid side converter, in which we saw that there are three control methods of grid side converter. First is grid forming control, second is grid feeding control, and third is grid supporting control. And we make a conclusion from that is the VSG is called as an upgraded voltage source based grid supporting control because it provides inertia additionally. So the first point is VSG, virtual synchronous generator, is called as an upgraded voltage source based grid supporting control. It is why it is called as an upgraded, because it provides inertia in addition. And second point is that virtual synchronous generator emulates the dynamic behavior of a synchronous generator, and from here we can say that the basic difference between the droop control and VSG control is that droop control only mimics the steady state characteristic of synchronous generator, and while the virtual synchronous generator control mimics both a steady state and transient characteristics of synchronous generator. So, and further we saw the principle of virtual synchronous generator control, in which we introduced with the function of swing equation block, governor block, QV droop block with PI, and further also we saw other inverter control methods with virtual inertia, which is analogous to virtual synchronous generator developed in the past, and the comparisons between them, and the some important names of other inverter control methods that is analogous to VSG are like one of the VSG developed by the VSY NEC project, and VISMA, that is called virtual synchronous machine control, developed by IEP, Institute of Electrical and Power Engineers, that is University Clausthal University, Germany. And another one is VSC control developed by KHY, Kawasaki Heavy Industries, and the last one is synchro inverter that we have seen in the first lectures. So in the second lecture, what we did is that we compared the droop control and VSG control to see the dynamic characteristics, to compare the dynamic characteristic between the two modes, droop control and VSG control. And in both droop control and VSG control, we saw two operations, that is in single inverter operation and parallel operation with synchronous generator. So in both operation, we compare the characteristics of droop control and VSG control. First one is single inverter operation, and second one is parallel operation with synchronous generator. And the motto behind the second lecture is that to understand the difference of two control methods caused by the presence of swing equation, that is the main cause of emulating the inertia in the inverter, and also see the advantage and disadvantage of VSG control over traditional voltage source based grid supporting control. And subsequently we also compare the dynamic characteristics of VSG control and droop control. A small signal models of both were also we saw in the second lecture. And in the second lecture we can make some conclusions like that. Third point is droop control is a particular case of VSG control in which both inertia and damping factor are set to 0. That is or we can in other words we can say that VSG, virtual synchronous generator, has larger inertia than droop control, and the amount of inertia in this VSG control depends on virtual moment of inertia, that is J, and the damping factor ratio depends on damping factor D, and the output reactance X also. And fourth point is delay in governor block reduces inertia and amplifies oscillations. And if we further want to emulate the governor, if we further want to emulate the delayed mechanical response of real governor of synchronous generator in the inverter model, then then it basically not improve the inertia. It reduces the inertia and amplifies the oscillation. So this is one of the important conclusion that we have seen, that and in contrary, if we apply the delay in the p omega droop block of droop control, then it increases the inertia in the droop control, and in VSG it decreases the inertia and amplifies the oscillation. And while in the, if we similarly, if we apply the same delay in the droop control of droop controller, p omega droop controller of droop control scheme, then it increases inertia and reduces the oscillation. And the last point is that output active power of VS is more oscillatory than that of root control. Uh, but this problem can be resolved by proper tuning of the damping factor and and the output reactance. This has been proved by the steady space analysis of the model that we can see in the last chapter. Now we come to the this what we are going to see in this lecture, and we will see the virtual inertia based stability and regulation support basically. And actually there are still some problem associated with virtual synchronous generator. So one advantage that unlike a real synchronous machine, the parameters of virtual synchronous generator can be controlled to enhance the dynamic response of system that is not available in the synchronous generator. So one of the big advantage that we can just play with the uh, play with the parameters of VSG and to enhance the dynamic responses of the system. So there basically there are many many enhanced, or you can say the new control mechanism based on the VSG, that some modification has been done in VSG to enhance the performance of the our VSG, so basic VSG. And the main motive is to enhance the performance of VSG to increase the micro stability and the regulation performance. Like first we can see in the first that what the authors had been done in that an enhanced VSG control is proposed to achieve the oscillation damping and proper transient active power sharing by the virtual state reactance adjustment. And this method is also a communication less accurate active reactive power sharing by enhanced VQ loop control and common AC voltage estimation. So this work has been done on the basic VSG control to increase the micro stability and to regulate the performance. And the second also new control mechanism is developed for a parallel operation of VSG and synchronous generator to prevent unbalanced synchronous generator current and inverter overcurrent. Basically, this has been done for the first one has been done for the islanded operation that is not connected to a grid, and this operation has some demerits. We connect the same grid to the VSG inverter. All in island operation, all the inverters are controlled by VSG. So there is another problem of unbalanced synchronous current and inverter overcurrent. So how to remove that problem? This method has been proposed in the past by some authors. So basically in this chapter we are going to see this first enhanced virtual synchronous generator control, which is mainly used to achieve which is mainly used to just remove these problems of inverter operations in the islanded operations, oscillation damping and proper transient active power sharing and accurate reactive power sharing to achieve these important 2 points. So basically the limitations of basic virtual synchronous generator control schemes are like oscillations. First one is oscillation active power sharing during a disturbance. Actually, the active power oscillation during a disturbance is a well-known feature of the swing equation. Thus, we can say that it is an inherent feature of real synchronous generator as well as a virtual synchronous generator. So it can be seen in both in synchronous generator and virtual synchronous generator. This is not a major problem in case of our grid synchronous generator alternator, because they usually have considerable overload capabilities, but interfaces in distributed generators are not high enough to ride through a large oscillations, because they can manage the large power oscillations. Synchronous generator can manage the large power oscillation, but our inverter interface distributed generators, they can't manage that. So this is the critical problem in in the case of our virtual synchronous generator, or we can say inverter interface distributed generator. And second one is that inappropriate transient active power sharing during loading transition. So this one is the one of the also major problem, that inappropriate transient active power sharing during load transition, in the case like if we increase or decrease the load, or we can say that loading transition, the case of island, when we disconnect or connect the grid, that is also comes under the loading transistor. In that case also there is inappropriate transient active power sharing. And the third one is this is the common problem in our microgrid, that errors in reactive power sharing, and this happens due to different line impedances that we already know. The different distributed generators are connected through different are connected through lines, and the lines are maybe of different length due to different location of our distributed generators. So this may cause errors in our reactive power sharing. So how will we remove these basic problems, these three problems of basic virtual synchronous generator controller scheme? The author has proposed a unique. The authors had proposed this enhanced VSG controller schemes, and in and the most important point is the most important point in the literature, what the authors had done to enhance the to improve the to manage the reactive power sharing, to improve the reactive power sharing. Most of the authors have preferred to do the eradicate this problem by communication channel. But in this enhanced VSG control, they don't use the communication medium. So this is better VSG control than the other that is based on communication based VSG, communication based inverter operation. So this is the block diagram of an enhanced VSG controller scheme. If we compare this block diagram with the block diagram of basic VSG control, there are two major modifications have been done, or we can say that have been added, like this. I also added this block diagram of basic VSG controller scheme. If we compare this block diagram, means slide number 6 or slide number 5, then you can see that a stator impedance adjuster and bus voltage estimator. The bus voltage estimator have been added in the enhanced VSG controller scheme, but that is not available in the basic VSG controller scheme. So if we can see the consciously both block diagram, we can see that in the basic VSG control, we are giving the measured output voltage like this. We are giving the measured output voltage directly to the here. V out directly given to the Q loop block. But in the enhanced VSG controller scheme, we are not giving the measured output voltage here directly to any Q drop. Here we are giving the bus voltage, estimated bus voltage to the Q drop block. So what we do, the first is to just sense the output voltage and current and convert into the alpha beta reference frame, and the power meter based on the measured output voltage and current in alpha beta frame, they calculate output active power and reactive power, and the bus voltage estimator just use this V out and I out in the alpha beta frame, and they give output to the Q block as estimated bus voltage. Here we are not giving the directly calculated bus voltage, calculated output voltage to the Q drop. So this is the major difference between the enhanced VSG controller scheme and the basic VSG controller scheme. And also in the basic VSG controller scheme, the reference voltage given to this PWM block is given by the Q drop plus PI block, and the phase angle is given by the swing equation function block. But in the enhanced VSG control mechanism, both reference voltage This VPWM and theta PWM is given by the stator impedance adjuster. So this is the another block added in the enhanced VSG controller scheme to just eradicate the I said earlier to eradicate three problems of basic VSG controller scheme. Now we will see the both working of both a stator impedance adjuster and the bus voltage estimator in detail. As I said earlier, that this point is the what I said. Proposed enhanced VSG control scheme has two major modifications that has been added in the basic VSG control: stator impedance adjuster and bus voltage estimator. And this figure number 3, the block diagram of a stator impedance adjuster. And if we look at this model, then what this model, how this model work, as we can see here, I out alpha and I out beta comes from the comes from the here comes from this ABC to alpha beta transformation, and this goes to the here we can see the stator impedance adjuster. This is the output measured voltage in the alpha beta stationary reference frame, and omega m is the angular frequency of the swing equation block, like this. This swing equation function, the omega m, the reference angular frequency given by the swing equation, and E and theta m are the reference phase voltage and angle given by the swing equation function block. And this is converted into the rho theta frame. Basically this is considered as rho theta frame, and this is converted into the alpha beta frame. We see the how this model works in the next slide, or in the upcoming slides, how this transformation works. So we get E alpha and E beta, and LLS is the virtual stator inductance. And one important point I left is that this is the virtual stator inductance that is added in the enhanced virtual synchronous controller scheme, but not here in the basic VSG controller scheme. LLS is not a actual component, but this inverter has a means it feels like that there is a inductor connected at the output of their at the output of the inverter. They don't, but there is no inductor connected here. How we just emulate this, that how this feels like there is inductor connected at the output inverter, we just use this stator impedance adjuster, so that we can eradicate the problem of active power oscillations and the proper sharing during the transient oscillations, proper active power sharing during transient. So LLS is the inductor in the virtual inductor, and omega m the angular frequency of the virtual angular frequency of the swing equation block. So by multiplying to this gives us like here v minus VLS alpha and VLS beta, and this is just added to the E alpha, and here it is subtracted to the E beta, and we get the reference voltage for our PWM block in alpha beta frame. And again this the reference voltage in alpha beta frame converted to the rho theta frame, so we get the actual reference voltage and phase angle for the PWM block, so that is generates that generates pulse drives for the inverter. So one thing here we can see that the virtual stator inductor is realized by multiplying the output current by the virtual stator inductor in the alpha beta frame. This is the one of the important point. And we can also say that this the function of the stator impedance adjuster is to adjust the output reactance of the DG freely and to operate as a virtual impedance controller, because this the work of a stator impedance adjuster is to just control the output reactance of DG, and it's operate as a virtual impedance controller, that it controls how it controls the output reactance of DG, that how means it sets the output reactance of DG. And the next we see voltage bus voltage estimator. This is the block diagram of bus voltage estimator, and this is simple working. This is very simple working, as we know that how to here what we have to use, that we have to just measure the resistance and inductance of line that is connected to our DG from the bus, from the PCC. So first we calculate R line and L line, and this R line and L line we calculate our bus voltage across the line and beta in alpha beta frame. Both has the bus voltage estimator and bus voltage estimator and stator impedance adjuster has both works on the principle of in the alpha beta frame. So first the output current is measured in the converted into alpha beta frame, and then here I used omega m to measure the voltage drop across the line through the inductance of line, and from here we get our the voltage drop through line in alpha beta frame, and this is subtracted in the output voltage of inverter in alpha beta frame, and from there we get estimated bus voltage in the alpha beta frame. And finally we again use the transformation block alpha beta to rate theta frame, so that we get the estimated bus voltage, and that is fed to the our Q Drew block. So here we by calculating the line voltage drop in the alpha beta frame using measured output current and line impedance data, the bus voltage can be estimated from the difference of output voltage and the calculated line voltage drop. Now the next slide is, so as I said earlier, this works in alpha beta frame. So the formula for measuring the output active reactive power is given by equation number 1 and 2. P out is equal to V out alpha I out alpha plus V out beta I out beta, and Q out is equal to minus V out alpha I out beta plus V out beta I out alpha. So this is the equations for measuring the output power in alpha beta reference frame. And these equation 1 and 2 are used by the block power measurement block in the enhanced VSG controller scheme. As I already said in the last previous slide, that a stator impedance adjuster works as a virtual impedance controller because it controls the output impedance of inverter. So we can say it as a virtual impedance controller of the inverter interface DG. And since we have used the transformation from rho theta frame to alpha beta frame, and inverse transformation used in the stator impedance adjuster, so how can we define this transformation? This is given below. For if we have rho theta frame, then alpha and beta, it is simply given by alpha is equal to rho cos theta and beta is equal to rho sin theta. So this is the major vector concept to get the alpha beta, and how to convert from alpha beta to rho theta. You can consider rho as a radius, so we can get alpha square plus beta square, and theta is the angle. So theta is equal to tan inverse beta by alpha. As I shown in the previous slide, that virtual stator inductor is realized by multiplying output current by virtual stator inductor LLS in the alpha beta frame. In the stator impedance adjuster, we saw that this is how this virtual stator inductor is how we realize the virtual stator inductor. And based on the state space analysis that has been done in previous chapter, tuning method of virtual stator inductor LLS is suggested to set total output reactance for both distributed generators to same large per unit value. Basically, this how we find this LLS. This is one of the major question, that how we are going to find this virtual stator inductor. So we have to do the state space analysis and of the model. So and on that model we get these equations xi star. What and how we set this value xi star is equal to 0.7 per unit. Here means this target value is proposed to 0.7 per unit because it is typical value for the total direct axis transit reactance of xd of a real synchronous generator. Here I have written in the fourth point because this is a typical value for total direct axis transit reactance xd of a real synchronous generator. So we set this xi star equal 0.7 per unit. And this approach increases our the active power damping ratio and shares transient load without oscillations. This is what we are doing, that is to achieve the our just to increase active power damping ratio and shares transient load without oscillation. And here we have to find out this LLSI, this point. I is for different, I just indicates for different distributed generators. And here the LFI and ZLNI, that is means L line I, are considered as a known parameters because we know these parameters LFI and LN line I, that is inductor of line, and this is inductor value of filter. So we know this value, and these S base I, omega mi, and U naught square we also know this value. So from here we can find out this LLSI value. This is virtual stator inductor. From this here we can find out. And S base for different distributed generators, this has different value. We get this different value LLS, virtual stator inductor. Now we see the bus voltage estimator. The principle of the bus voltage estimator is similar to that of a stator impedance adjuster because they just both use the alpha beta reference frame, and by calculating the line voltage drop in alpha beta frame using measured output current and line impedance data, the bus voltage can be estimated from the difference of output voltage and calculated line voltage drop. Since the line to line RMS value of estimated bus voltage for each distributed generation should be approximately equal, this V bus, what we get estimated data, should be approximately equal because this is the bus voltage, and bus voltage can't be changed for different generation. So it should be approximately equal. What we estimated, it should be approximately equal. Accurate reactive power sharing can be obtained by using estimated bus voltage as the input reference of Q group instead of respective output voltage of distributed generation. So this is the Q group block of enhanced VSG control. In the basic VSG control, we are giving the output, just giving the output voltage of inverter here, feeding to this here instead of the estimated bus voltage V bus star, V bus cap. And the working, I already explained how this work, Q2 block, the function, how this Q function works as a how this will set as the reference reactive power for the inverter. However, if we it may be happened that this bus voltage estimators might be wrong. So there might be a chance of reactive power sharing error. So we will see that in the next slide. And this whole block diagram just we can write in the mathematical equation like this: Q reference is equal to Q naught minus KQ V bus cap minus E naught. So this is the modified Q group controller that is given in equation number 4. And if there is an error in V bus cap, if we estimate if we estimate wrongly in the V bus estimation, then it will cause reactive power sharing error. Suppose let it may be case that V bus star cap, and that is V bus star cap plus delta V1 star cap, and V was 2 delta V was star cap plus delta V star cap. So there the estimation estimation at bus voltage for two distributed generation is different. So if we substitute this V was star cap and V was 2 star cap here in equation number 4th, then we get and just subtract this Q reference 1 and Q reference 2 star, then we get this number equation as equation 5. So this is the different reactive powers reference set by the distributed generation by the inverter control. So if we in a steady state, what we get Q reference I star is equal to Q out I star. So we can say that Q out I Q out 1 star minus Q out 2 star is equal to this. So we can say that the reactive power sharing error caused by the estimation error is determined the QV VQ group gain KQ star. And we know that output reactive power through the inverter we can calculate as this is the set value of reference virtual voltage given for the inverter, and V was is the voltage the bus side, or we can say at PCC, and delta is the phase difference between the E and V was. So this we can get the output reactive power from the inverter. This is you can say that EI is the output of the inverter and V was is the V was is the voltage at the bus or PCC, and XI is the inductance between the inverter and the PCC bus, and this value is approximately equal to the filter value and reactance of filter and reactance of line plus reactance of line. If we do the small signal analysis of this equation number 7, we can write this as take the differentiative and delta Q out I E minus V was cos delta I del EI. As xi is constant, so it is written as it is, and the numerator will be changed. So first we will take this part. So first we'll here we'll differentiate this part and EI, then here it is delta EI, and this part I just remain as it is, and here EI and differentiate again this. So we get delta EI minus delta V was cos delta I. As we know that this phase angle is very small, so we can write cos delta I is approximately equal to 1, and we can also take approximation like that EI is some is approximated to V was, or we can take it as a reference equal to reference value U naught. We take a constant value U naught, and it can be simplified as if equation number 8 like that delta Q out I E naught into delta EI minus delta V was. So with 9, a small signal model of the reactive power control part is shown in figure number 6. So from this equation we are going to make the block diagram. This is the block diagram that what we derived in the equation number 9. And from this small signal model of reactive power control loop, we can make the Bode plot. So here the Bode plot for both VSG and basic VSG and enhanced VSG, and here with filter and without filter. Here they are written as open loop or plant plus filter. Open loop means they are considering just as it is upper side. They are not considering this filtered side. So basic if we see magnitude and phase angle, in phase angle There is no difference between the basic VSG and enhanced VSG. Both have same. If we see the plant and filter, that is closed loop system, they both have same phase angle, and in the basic VSG and enhanced VSG, or that in open loop system, that is we not consider the feedback, that is not consider this filter section. So this has also the same line, the same diagram. And if we see in the magnitude curve, this is the lower lines, this one, basic VSG for open loop and enhanced VSG for open loop, but there is no feedback. So you can see this also has approximately same curve. But if we see that basic VSG plant and filter and enhanced VSG plant and filter closed loop, they have major magnitude difference between them. So from this body plot, we can say that the increased output reactance by adding virtual stator inductor LLS causes a decrease in the reactive control plant gain. Here you can see that this blue curve is for the basic VSG, and this and this green curve is for enhanced VSG, and there is a there is a there is a difference in their gain. So here this occurs because of our virtual stator inductor LLS. So from the body diagram we can see here. And now we just applied what we have already see the various models, and how to find out parameters and a small signal analysis, and just we will apply this also all enhanced VSG control in this simulation circuit. So this both DG are operated by enhanced virtual synchronous generator controller scheme, and the KVA base for first inverter is 10 kVA, and the KVA base for second inverter is 5 kVA. And we have taken the inductor value for both DGs as same, filter values, filter side both is same, but for the line, if we see the line, line is also same of same value. But if we find out the base value, if we find out the if per unit value, then it will change, because the KVA value is different for both DG. And similarly we will find out the virtual stator inductor by the mechanism, as I discussed earlier. And this is circuit breaker, and the load is connected at the PCC. And here grid is also connected to see that means here author what has described that they have taken grid as a loading transition, means from islanded to grid connected, and grid connected to islanded. They see the oscillations in the active and reactive power sharing. So here the grid is connected. And now we see the simulation results. We can from the simulation result we can verify the effectiveness of proposed enhanced VSG controller scheme over the basic VSG controller scheme. And here authors has taken three cases. First case is that islanding from main grid at 21 second, that this disturbance is created at 21 second, and in that case they are disconnecting the system, they are disconnecting the grid from the system microgrid. So islanding at 21 second, the system went into islanding condition, and at 24 second, at 24% there is loading transition, and at 27 second intentional active power sharing change, means we are changing the value of P reference 1 and P reference 2, means P omega drop block, we are just set the value of active power but they have to deliver. So here at 27 second we are intentionally changing the active power from both the DG, so we get the disturbances. So here then the authors has compared these simulation results in three cases. That first one is for basic VSG control. Here is no enhanced VSG control attached here. So you can see there is a large oscillations during active power and also in the active power sharing. And second is for basic VSG control with a stator impedance adjuster. And in second control, there is no bus voltage estimator attached. And in third, enhanced VSG control means both a stator impedance adjuster and the bus voltage estimator both are attached. So if we compare A and B, we can see the oscillation has largely damped out in the case of second because of a stator impedance adjuster. They are because we just enable them in the inverter control due to just proper active power sharing and during transient and to damp out the oscillation of active power sharing. So it easily they are working in good condition. And at the 27 second, we can see that the by the change of active power set value of distributed generator 1, which is not a loading transition, the active power solution cannot be eliminated in this case. Means here at 21 second and 24 second, we can see that active power sharing eliminated rightly in correct way. But at 27 second, their disturbance has not been oscillation has not been purely damped out because this is not a pure loading transition. In the at 27 second, we are just changing the active power sharing. So this is not loading transition. So active power. So the oscillation has not been damped out. Has been not damped out in proper manner. And this is omega 1 omega reference omega m, this angular frequency set by the inverter control. And for the reactive power, we can see the whole how the oscillation has been damped out. And in the second case, the same the same the same diagram we get for the reactive power, but with proper damped out the oscillations. And in the third case, what we get proper reactive power sharing because we have enabled the bus voltage estimator, and bus voltage estimator was to reduce the reactive power sharing error. So in the third case, we saw there is a proper reactive power sharing error than compared to first and second case. That in that is in VSG, basic vertical single generator control and basic vertical single generator control with a static impedance adjuster. They don't able to do uh, the reactive power sharing properly, and in the enhanced VSG control, they are doing reactive power sharing properly due to the bus voltage estimator. And we see the zoom in simulation result of reactive power and voltage of distributed generation at 24 seconds. So we get more properly concise results. The first one is for basic virtual synchronous generator control, and second one is for enhanced virtual synchronous generator control. So this is key difference, and here we get the reactive power, a high oscillations in the output reactive power. And for the here we can see that the reactive power set by the inverter control is damping out sometime, and subsequently we are getting the damped out reactive power at the output. And even in the virtual voltage set by swing equation block, and VPWM is the given to the upper PWM block, and V out one is the outputs of the inverter. So here we can see there is a large oscillations, and even is large even has larger value than the output of PWM inverter and V out one. Because in this second part enhanced VSG control, we set the even from the stator impedance adjuster, not by the swing equation block. But here we are setting the even value from the swing equation block, and but in enhanced VSG control, it is set by the stator impedance adjuster. Finally, even is set by stator impedance adjuster. So we get this type of curve. What? Why it is structuring? So coming to the conclusion section. So what we can conclude from our discussion in this lecture, that here the author has developed a communication list based enhanced VHG control method, and in which they have used a stator reactance adjuster to based on a stat space analysis, which enable active power damping and proper transient power sharing. And improved vehicle group control and common AC bus voltage estimator is proposed to achieve accurate active power sharing. So, so the communication. This is the conclusion from the this lecture. That's all. Thank you.
साहिल
Yes, sir.
साहिल इसके
Yes,
अंदर जो इन्होंने लाइन इम्पिडेंस के बारे में बोला था, तो have they given the line impedance parameter? So they have even asked to told the method that how we can estimate it.
line impedance parameters means, yes, they told about how to calculate the means line impedance value.
Okay, okay. I mean, is it through that Bergeron model based frequency response, or just they have just mentioned that we have used some method and these are the line values which we have used?
Means this value, sir, virtual inductor value.
No, I'm talking about the line values, this 0.14 and 0.015. So
Yes,
this is something which they have already given, I guess.
yes, sir. This is already given, and they tell the methods how we calculate this value. There are some methods they have mentioned, sir.
Yeah, yeah, some frequency response based methods are there. Okay,
Yes, sir.
okay, 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 ठीक है, ठीक है, okay.
Thank you.
Hmm.